Okay, hello everybody. So I'm actually going to do part B first. When does it make sense to change variables in your integral to spherical coordinates? So I'll start with words. There are two reasons. First reason, the region of integration, the region you're integrating over, becomes easier. Hopefully, when in spherical coordinates, we're having three-dimensional integrals, so a three-dimensional rectangle. You could call this a rectangular prism or something. And let's just draw a picture of this. So like something like this would be great to integrate over this if this is like A. And this is maybe the R theta phi space or something. Then our parameter, or our changing to spherical, maps this over to XYZ space, where now the image of our nice rectangle is the original thing we were trying to integrate over. Maybe it's some weirdly shaped object over here. Who knows what it looks like? And we had some function that we were trying to integrate. So, this integral was hard because this region was hard. Yeah. So this is what? XYZ space. And this was the R theta phi space. They're both R3. But, maybe I'll add in words that G distorts volumes, since that'll be important for part A. Okay, so what's the second reason? Reason number 2. So first, the region could become easier, but then also the composed function could become easier. That's the second reason, namely this function, f after g. So let's even put a formula. What is that composed function? Well, f after g. First you do g, then you do f. And that gives a function sending r theta phi to some number. Okay. Good, so let's, the price we pay to make things easier, the price we pay is we need to change the volume. So there's some factor we have to compute that will fix this distortion of volume from A to B. So part A, compute the change of volume factor for spherical coordinates. And they give us the map, so we don't need to derive this map. What I'm going to do is I'm going to call it theta 1, theta 2, just because it's going to be way easier than theta and phi, those two Greek letters. And let's call this map G, because that's what I called it up here. And it sends, now, r sine phi cos theta will be r sine 2 cos 1. R sine 2 sine 1. That's what I'm just renaming this. You can name things however you want, provided you write down a map that makes sense. And RC2, because phi was now going to be my theta 2. And I'll write that sort of like, this was the old theta, this was the old phi. Okay. So now, remember the formula is the square root of the determinant of the gram matrix of, now how many columns of the Jacobian? There's going to be a first column of the Jacobian, a second column from the second input variable, and a third column from the third input variable. So this will be a 3 by 3 matrix. And then we take the determinant and take the square root. Okay, so what's W1? W1 is, partial r. So I'm going to write partial r to remind me where W1 is coming from. Maybe I'll write it down here, partial r. So here I get an S2, C1. Partial r gives me an S2, S1. Partial r gives me a C2. W2 is from partial theta 1. And theta 1 derivative, a cos becomes minus sine. And then the r S2 hangs out. Those are constants with respect to theta 1. Okay, theta 1, a sine becomes cos. And then the r S2 hangs out. And here, theta 1 does not appear, so this is a 0. So now I take partial the third variable to get my third column of the Jacobian, which will be, okay, S2 becomes, or sine becomes cos. Sine becomes cos. And here cos becomes minus sine. Okay, so you have to take these partial derivatives correctly. Otherwise, I have no idea if you know what's going on and how we'd get them. So be very careful with your cosines and sines and minus signs and all this stuff. Okay, so now we compute the gram matrix. Well, that means we compute some dot products. This dot itself will be S2 squared, C1 squared, plus S2 squared, S1 squared, plus C2 squared. Factor out the S2 squared, leaving a C1 squared plus S1 squared, but that is 1. And again, we have now an S2 squared plus C2 squared, which is again 1. So the answer here is 1 for that dot product. Let's take W1 dot W2. That means I go here, plus here, plus here. And then if you stare at this long enough, you realize that these are the same, but with opposite signs, and they cancel. The last term is C2 times 0, which is a 0. And so this whole thing is a 0 dot product. Okay, let's take W1 dot W3. So that's now this one times this one. Okay, R C2 C1 times S2 C1. You have to just do this yourself and make sure you're careful. And now the last one is a minus. Okay, so now I have to simplify, and I notice that I can pull out a common factor here of what? Maybe a C2, RC2S1, RC2, or I don't know what it is. It's okay, it's probably going to be this, so it can cancel. S2C2, yeah, R, S2, C2, R, S2, C2. Okay, so after staring for a while, you realize that R, S2, C2 can be pulled out, leaving a C1 squared plus an S1 squared. This becomes 1. And then I have an R, S2, C2 minus an R, S2, C2, and the whole thing is 0. Great. So that automatically means we have a 0 down here and a 0 down here. Let's take W2 dot W2. So now we're taking this dot itself. Now I can pull out an R squared S2 squared, and I get an S1 squared plus C1 squared left over. That becomes a 1. And that is as far as I can simplify W2 dot W2. W2 dot W3. It's going to be this. Okay, what is that? Minus R squared S1, S2, C1, C2. Then this piece is plus R squared S1, S2, C1, C2. Excellent, because those cancel. And then the last is 0 times that, which is just plus 0. This whole thing is 0. Excellent, so that means this one is 0. Very last one, W3 dot W3. Okay, so sum of squares. Now I factor out the C2 squared and the R squared. And I get a C1 squared plus an S1 squared remaining. That becomes a 1. And I get, now I factor out the R squared from these two terms. R squared, C2 squared plus S2 squared. This becomes a 1, and this is an R squared. Excellent. Here is my 3 by 3 matrix. You'll notice that all the entries are 0 off the diagonal, so the determinant of this matrix only has one non-zero term, namely the multiplication of these diagonal elements. So this whole square root is just going to be the square root of the determinant of this thing, which will be 1 times R squared S2 squared times R squared. So that's going to be an R to the 4th S2 squared. Taking the square root brings me down to an R squared sine of theta 2. That's the answer. We're all done. So you change to spherical to either make the region easier or the function easier. The price you pay is you must account for the distortion in volume of your change of coordinates. Okay. Great.